This is the lecture for lesson 21. This section is going to continue with polynomials, but also discuss power functions. And we're also going to discuss the end behavior of those polynomial functions. So what we will do in this part is identify if we have a power or a polynomial function, identify if the graph is a polynomial function, and then determine end behavior. So the first thing we need to determine is, do we have a power function or a polynomial function? Polynomial functions are the ones we've been working with. For example, they're going to have multiple terms. So ax squared plus bx plus c, that's a polynomial function. We are going to have more than one term, and they all have to be powers of x. A power function is only going to have one single term, and it is going to have a number and just an x to a power. So looking at our first examples here, do we have, in step one, do we have polynomial function? So in order for it to be a polynomial function, it should be something x to a power plus something x to a power plus something x to a power, so on and so forth. So looking at A, there's a square root in there. No, square roots are not polynomial functions. If I look at B, I've got a fourth power, an x, a number, multiple terms raised to powers. Yes, that is fine. C, it looks like we're factored here. So let's distribute this out. Negative x squared times x is negative x cubed. Negative x squared times negative 7 plus 7x squared. Yes, that now looks like a polynomial function. In 2, they want us to identify which ones are power functions. So if there's more than one term, automatically not a power function. So looking at A, I have 2 terms. No. 2 terms separated by a addition or subtraction sign, I should say. Because in B, these 2 terms are being multiplied, which simplifies to 20x to the 7th, a single term, which this is now a power function. C has a square root, so no, those are not polynomials or power functions. So do I have a polynomial graph? Do I have a polynomial function? Well, here's what's going to happen in a polynomial function. They're going to be continuous everywhere. So that means it's a smooth line or curve. You're not going to have any breaking, jumping, or what we call asymptotes. So looking at the image here, I'm showing you examples of a 0 degree, 1st degree, 2nd degree, 3rd degree, 4th degree, and 5th degree. So basically, the polynomials we're going to be looking at are nice, smooth curves. There's no corners. There's no jumping. There's no breaks. Looking at these graphs, we need to determine which are not polynomial functions. So it's not going to be a polynomial function if it has a corner or a break, or is not a smooth curve. Well, B is not smooth. There is a corner here. That is not a polynomial function. C has a break here. This graph breaks right here. So B and C are not polynomial functions. Now, given the power and whether we have a positive or negative leading term is going to determine what we call the end behavior of our functions. And both of these images show the same thing. So for an even degree polynomial, so the highest power is 2, 4, 6. What's going to happen if your leading term is positive? It's going to open like this. It's going to be up on the end, up on the end. So you can kind of see that over here. That corresponds to this first one here. We don't know what happens in the middle, but in the end, it's going up and it's going up this way. So as I go to negative infinity on the x, my graph goes to positive infinity. As I go to positive infinity on the x, my graph goes to positive infinity. So that changes if it's now a negative. If I put a negative in front, my graph is going to open down. So power 2, 4, 6, even powers are now going to have it flipped. So instead of opening up on the ends, it's going to open down on the ends. So as I go to negative infinity, it's going to go to negative infinity. As I go to positive infinity on my x's, it's going to go to negative infinity or down. Odd degrees, so 3, 5, 7, those go in opposite directions. So you can see here a positive is going to be in generally this form of a shape. So here's the third one. It's going to go down in this way, and it's going to end going up. If I have a negative in front, it's going to flip-flop it. So it's going to go up on this side and down on that side. This works for every single odd and even powered polynomial, given it's positive or negative. So what we need to do is we need to determine the end behavior of each of these graphs. We have 3x to the 4th. So what I see is I see even power, and it's positive. So even power, positive, means it's going to end like this. So the way I write that is as x goes to positive infinity, the function also goes to positive infinity. And as x goes to negative infinity, the function goes to positive infinity. So as I move to the right, it goes up. As I move to the left, it goes up. That's those two statements. Five, determine the end behavior of negative x to the 7th. So we have an odd power and we have a negative, which means it's going to go like this. So as I move to the right, x goes positive, the graph goes down or to a negative infinity. As I look to the left, my graph is going up. So the function goes to positive infinity. These will always stay true. So if you have that chart written down, you can just compare and copy the answers of how you write your end behavior here. Number 6, find the end behavior of x to the 11th. Well, that's an odd power, but it's a positive, so this one's going to go this way. So as I go to the right with my x's, my graph goes up to positive infinity. And as I go left on my graph goes down to negative infinity. Which means the last one is probably an even power with a negative in front. So even power, it's negative 2x to the 4th, so negative in front. So instead of opening up, they're both opening down, which means that as I go to the right with my x's, the graph goes down. And as I go left on my x's, the graph goes down. And if you compare, if you go back here, all of these should match with exactly what these say here. This next portion talks about local behavior of polynomial functions. So we'll be looking at intercepts, x and y intercepts from factored form. We'll discuss how the degree relates to turning points and the number of x-intercepts. We can factor to find our zeros or x-intercepts, and also talk about multiplicities. These first three, we have factored form polynomials. And we know from prior section here in this module that when we graph, or we had the graph, and we said maybe this is 1, 1, 2, 3. We said it crosses at x equals -1, so the factor is x plus 1. If this crosses at x equals 3, the factor is x minus 3. Well, now we're going to do the exact opposite. We're given factored form and want to give the zeros. So this means real easily here, the x-intercepts are, if this is negative 4 inside here, it's positive 4, 0. If we have x minus 5, that's a positive 5, 0. And if we have x plus 5, that's negative 5, 0. So you just take those values out. Now, to find the y-intercept, what you're going to do, plug in 0 for x. So that one's going to take a little bit of work. So negative 2 times 0 minus 4 squared, 0 minus 5, 0 plus 5. So that's negative 2 times negative 4 squared times negative 5 times 5. So I have negative 2 times 16 times negative 5 times 5. That gives me 800. So the y-intercept for this one is 0, 800. Okay, let's look at number 2. We have an x on the outside, so that means x is 0. So 0, 0. X plus 2 means the value is negative 2, and x plus 1 means the value is negative 1. So remember, if you have the factored form, the 0 is the opposite of what's listed. And if it's just an x, you get 0. So if I want to find the y-intercept here, I'm going to plug in 0. So 0 cubed, 0 plus 2 squared, 0 plus 1. Well, this is 0 times anything is going to be 0. So the y-intercept is 0, 0. There's actually no work for that one. All right, let's look at number 3. So we have x plus 3 as a factor. So the x-intercept is negative 3. If we have x plus 1, the x-intercept is negative 1. And if we have x plus 4, the x-intercept is negative 4. And then if I want to find the y-intercept, let's plug in 0. So I got 0 plus 3, 0 plus 1 cubed, and 0 plus 4. So 3 times 1 times 4 is 12. So the y-intercept is 0, 12. Another thing we can determine is the number of turning points. A turning point is a point of the graph where the graph changes from increasing to decreasing or decreasing to increasing. So going from up to down, this is a turning point. Going down to up, that's a turning point. Given your degree, you have one less than that number of turning points. So if you have a degree 4, you are going to have 3 turning points. So take away 1 from the highest power degree you see in your polynomial. That's how many turning points you have. Or you can have, let's put it that way. So the first function, 2x to the 4th minus 4x squared plus 1. So we have degree 4. There's our highest power right there, which means the max number of turning points is 3. B, x cubed plus x squared minus 2x plus 1. We have a degree 3. The highest power is 3. So the most amount of turning points we can have is 2. 1 less than that. Last one is x to the 5th minus x to the 3rd minus 1. So our degree in this one is 5, meaning we could have 4 turning points. Given a polynomial function, we can factor it to find all of our zeros. So we're going to think back to what we did in the first module and factor these guys to see what we can get. So if I work with this first one, x to the 3rd plus 4x squared plus 4x. 3 terms, which means I'm going to follow trinomial rules, except for the fact that I have a GCF first. So the first thing I'm going to do is take out an x, leaving me with x squared plus 4x plus 4. And now I'm going to follow my trinomial rules. Is there a pair of numbers that adds to 4 and also multiplies to 4? Yes. 2 plus 2 is 4, and 2 times 2 is 4. So there is the factored form. And once I'm in factored form, I can find my x-intercepts. So factored form, that means x equals in the front 0. And this one is, if it's plus 2, negative 2. This one is also negative 2. I don't need to write it a second time. Okay, let's take B. X to the 4th minus x squared, 2 terms. So it's probably going to be a special case, but I also see I have a GCF. So I'm going to take out the x squared first, leaving x squared minus 1. This is a difference of squares. That's a special case. X squared is x times x, and 1 is 1 times 1. 1 gets a plus, 1 gets a minus. So the x-intercepts here, we're going to cross at x equals 0. We're going to cross at negative 1, and we're going to cross at positive 1. Because again, this first one is 0. Set this one, gives me negative 1. This one gives me positive 1. If you don't remember how to do that, remember we're just setting each piece equal to 0 and subtracting or adding over. That's how I'm getting them here. And then the last one has 4 terms. So 4 terms means I'm going to do grouping. So x cubed and 5x squared, I can take out x squared. It's going to leave me with x plus 5. Now I want to be left with x plus 5 over here. So what did I pull out? Well, I pulled out a negative 9. Because negative 9 times x is negative 9x. Negative 9 times 5 is negative 45. So I have x plus 5 and then x squared minus 9. Okay, well, x squared minus 9 can go further because that's perfect squares. X squared is x times x. 9 is 3 times 3. 1 plus, 1 minus. So in this case, my x-intercepts are going to be at negative 5, negative 3, and positive 3. Now, the one thing we haven't talked about yet is what is called multiplicity of a 0. So looking back at what we did here, when we worked with B, we had x squared, x plus 1, x minus 1, and we said our zeros were 0, negative 1, and 1. Now, according to the fact that this is a power 4, I should have 4 zeros. The highest power is how many zeros you should have, but I only found 3. That's because this value of 0 here is actually a multiplicity 2, meaning that 0 happens twice. And that is going to impact how our graph looks at that spot. So if I'm working with a multiplicity and that multiplicity is even, so it happens twice. It's a multiplicity 2, a multiplicity 4. What's going to happen is it's going to hit the graph and bounce back. It's not going to go through the axis. Versus if it's an odd multiplicity, so it happens 1 time, 3 times, then it's going to go through the axis. So by looking at this graph, we know that this is an odd multiplicity. And looking at the graphs here, this is an even multiplicity. And I can go the other way, is if I know I have an even multiplicity, I know it's going to hit and bounce back, versus an odd multiplicity, it's going to go through. Here we see an example of a function with what's called 12 real roots. How do we know there's 12? Well, this one here, x to the 3rd power, is going to give me 0. Because it's to the 3rd power, it has a multiplicity 3. This one here, x plus 2, if I solve that, is going to give me negative 2 as a root. Power 4 means multiplicity 4. And this last one, x minus 3, gives me 3 as a root, multiplicity 5. If I add all of these together, I get 12 real roots. So this is a function that is x to the 12th power. So there are 12 zeros. The thing is that some of them only can happen more than once. So the value of, if I look here, -2 was a multiplicity 4, an even multiplicity. So the graph is going to hit the x-axis and come back up. It eventually has to make its way back down to the x root of 0, which is a multiplicity 3. Odd means it goes through the graph. The graph can do anything it wants over here, but eventually has to come back up to this final 0 that's over here of odd multiplicity. So it is then going to go back through. So I know from the equation, I can make my graph and what the multiplicities are and what the graph would look like at each of my zeros. I can also look at the graph and determine that backwards. So I know this is going to be an odd multiplicity. This is an odd multiplicity because it goes through. This one has to be an even multiplicity because it bounces back. So let's take a look. In number 6, the function is -x² times x plus 2 times x minus 2. Well, this one here is going to be x equals 0. And because it's power 2 means a multiplicity 2. X plus 2 gives me the value x equals -2. I don't need to write a multiplicity because it just happens one time. And then x minus 2 is a factor. It gives me the x value of 2. Again, single multiplicity, so I do not need to write it. In 7, our equation is -3x to the 3rd, the quantity x minus 1 squared, and then x plus 3. So working with this first piece is going to give me the x equals 0. Because it's to a 3rd power, it's multiplicity 3. Next one, x minus 1 is going to give me the value +1. Because it's squared, it is multiplicity 2. And then the last one, +3. X plus 3 means the value is -3, and there is no power, so I don't need to write anything. Okay. Number 8 gives us the graph, and it says we have a degree 4. So find the zeros and their potential multiplicities. Well, we hit the axis at -1 and at +1. Now I said hit the axis. So we hit the axis and bounce back. It means it has to be an even multiplicity. And if we have a total of degree 4, these both have to then be multiplicities 2. I have 2 roots. They both hit and bounce back, so they both have to be even. 2 plus 2 gives me my entire degree of 4. Now we're going to put it all together. We're going to look at graphs and pick out the turning points, the zeros, the roots, and we're also going to make the graphs from our functions. We have 2 graphs here. We want to discuss what can be concluded about the intercepts and the turning points. So I'm going to start with the intercepts, or where I hit the x-axis. So the x-intercepts are going to be at -1, 0, and 1. -1, it passes through, so that's going to be normal. 0, it bounces back. So this has to be a minimum multiplicity 2. And then 1, it goes through. So we're going to leave that as a single one because we want to know just where we can start with. So 1, 2, 3, 4. So it's got to be at least a 4th degree. And we have 3 distinct zeros. Okay, turning points, we have 2 of them, right? Or 3, nope, we have 3. So if it's at least 4th degree, we should have 3 turning points. So here we go from up to down. Here we go from down back up. And here we go from up back to down. So concluding all of those things together, x-intercepts, multiplicity, and turning points. Looking at the second one, we're going to hit the axis or cross the axis here. Let's see, that's -3 and it goes through. So I'm going to leave it as a odd. We're going to leave it like that. At 1, we bounce back. So this has to be, we're going to estimate multiplicity 2. So we're just going to say either 1 or 2. So if we have a single root and a double root, we probably have a third degree. And if we have third degree, we should have 2 turning points. So 1 here where it goes from down to up, and then 1 here where it goes from up to down, 2 turning points. So now we need to use what we know to be able to graph the polynomial. So one thing I know here is a y-intercept is -4. So 1, 2, 3, 4. We're going to cross the y-axis at -4. I'm going to factor it so that I can find my x-intercepts. So if I have 4 terms, x cubed plus x squared minus 4x minus 4, I need to group. In the first 2 terms, I can take out x squared. Leaves me with x plus 1. In the second pair of terms, I can take out -4, leaving me with x plus 1. So that means we have x plus 1 and x squared minus 4. Well, x squared minus 4, we know are both perfect squares. So x squared is x times x. 4 is 2 times 2. 1 is plus, 1 is minus. That means my x-intercepts are -1, -2, and 2. So -1, -2, and 2. Okay, some other things we need here. We are an odd positive, meaning it's going to go like this and then like that. So on the end, it's going to go down, and on the positive end, it's going to go up. So we know on this side, it's going up. On this side, it's going down. All of my zeros are single roots, meaning that I'm going to cross through the axis. So I have to cross through the axis, turn it back to hit the next 0. I need to at least go down to the y-intercept, turn, and come back up. So I'm trying to create a smooth curve connecting what I know, remembering that all of these are single roots, so we have to cross through. Also remembering that if this is a third power, we have 2 turning points. So I turned here, turning point 1, turning point 2, and there is a rough sketch of my graph. Next problem, and this should say -x⁴ plus 4x squared. I lost my squared. All right, there is no number on the end, which means the y-intercept is going to be 0. I have 2 terms here, so I'm going to first start with seeing if there's a GCF. And I'm going to factor out -x² because I want to pull that negative out. So if I take out 2 of the x's when I had 4, there's still 2 left. 4 divided by -1 is going to leave me with -4. So I have -x², and then this inside is going to factor to x plus 2 and x minus 2. Meaning that our x-intercepts are 0. This one, though, has a power 2, so it's multiplicity 2. We have an x value of -2 and an x value of positive 2. Each of these are single roots. Remembering we have a 4th degree. So 4th degree negative, meaning it's going to look like that, ending down in both directions. And I should have 3 turning points. So let's mark our zeros here. -2, 0, and positive 2. Knowing that it has to go down on this side and down on this side. Okay, so how am I going to connect this? Knowing that I have to cross through because these are single roots, but 0 is a double root. So what that means is I'm going to hit the axis and go back. So if I'm above it here, I'm going to hit it and bounce back up. And I'm going to connect those. So here, if you look, I've got turning point 1, turning point 2, turning point 3. And I have a 4th degree ending negative. You can always use a graphing calculator when you're done to double check it, but we're just looking for a general graph here. Now we're going to be given the graph and asked to write the polynomial function. So what we're going to do is we're going to find all of our x-intercepts and determine what's happening in each of those. Are they single multiplicities or double multiplicities? Because that then determines if we put a power on the root. And then we're going to find the polynomial of least degree. So we're only going to worry about, we're going to say if the root happens once or twice. That's it. So it's either a single root or a double root. And then if there's any other y-intercept that we need to figure out, it'll help us determine if there's a stretch factor. So here we have a graph, and we're going to start with finding the x-intercepts. So we're hitting at 0, but it hits and comes back. So that means it's a multiplicity 2. And we also have a root of 4, which crosses through, so multiplicity 1. So what that means is anytime an x-intercept is 0, it's a factor of x, but this is happening twice. And then we also have a factor of 4, a root of 4, 0 of 4, which is a factor of -4. So if I multiply these back out, I'm going to get x cubed minus 4x squared is going to be my function here. And one way I can double check it is there is nothing on the end here. There's a 0, and that is where my y-intercept is at 0. So I know my graph is correct. Next graph. Let's find where it hits or crosses the x-axis. That is at -1 and at +1. And at each time it hits means they're multiplicities 2s. So if the answer is -1, its factor is +1, which will be squared. And if its root is +1, its factor is -1, and we're going to square that. Now, depending on Newton's system, it may let you enter it this way. If not, we can FOIL these out. This first one's going to turn into x squared plus 2x plus 1. The second one's going to turn into x squared minus 2x plus 1. And then from there, I'm going to have to distribute out further. So if I take x squared through, that's going to make x to the 4th minus 2x cubed plus x squared. Then I'm going to distribute the 2x through. So 2x times x squared, 2x cubed. 2x times -2x is -4x squared. 2x times 1 is 2x. And I'm stacking vertically so you can see how my terms will line up to combine. So 1 will go through here. So that's x squared minus 2x plus 1. So let's see, that's x to the 4th. These guys cancel out. 1 minus 4 plus 1 is -2x squared. The -2x and +2x cancels out, and then plus 1. And if we verify here, plus 1, it crosses at y equals 1. There we go. This is going to be just like the last one here. Find the equation of a polynomial of degree 4 if your zeros are x equals 0, x equals 3, both have multiplicity 2, and your y-intercept is 0. So that means all we need to do is work with these, multiplicity 2. So if x equals 0, that's a factor of x squared. If x equals 3, that's a factor of x minus 3 squared. So let's see, if I multiply or FOIL this out, that's going to be x squared minus 6x plus 9. And then I can distribute the x squared in. So x to the 4th minus 6x cubed plus 9x squared. And then the last problem from this section, I know this is a long section and there's a lot of different topics here. Again, a polynomial of degree 4, zeros at x equals 0 with multiplicity 3, and then an x equals 1. So if our factor, or 0 is x equal, or 0 is at 0, the factor is x, but it's multiplicity 3, so it's going to be to the third power. If the 0 is positive 1 here, our factor is negative 1, x minus 1, and it's a single root, so just write it one time. And then distribute these out. So x to the 4th minus x to the 3rd. I am done because I know it's a degree 4. So that is the end of this section. You can go ahead and do your homework.